All right, well, now that you've learned the three fundamental methods of integration, of course, basic, substitution, and parts, we're going to move into the next phase of integrals and solving differential equations. We're going to learn that there's other specific kinds of equations that require other methods, which still might mix and match basic, substitution, and parts. So our first type is going to be the type that is called separation of variables. Simply put, an equation that has that can be expressed as a product of two functions, and each function being in terms of a different variable. Basically, x and y together. X and y mixed together into the same equation. Now, separation of variables is actually doing implicit differentiation backwards. Do you remember implicit differentiation from Chapter 3? It was quite challenging. Actually, doing separation of variables, doing it backwards, isn't quite as challenging. We just have to understand that we're going to need to separate the x and y. So here's a kind of a good starter basic equation. X and y are together. And what we need to do is still solve this differential equation. Now, it's actually going to always be the case that what you're going to do is put the x's on one side, and you're going to put the y's on the other side. And these two arrows both insinuate algebra. The red arrow is, of course, multiplying. The green arrow is dividing. So once we divide y to both sides, we get 1 over y. And once we multiply dx to the other side, we get 2x dx. Now, really, all we want to do is integrate each side. It's kind of like having two problems for the price of one. And so we're going to do the antiderivative of both sides and come up with our solution. Now, the antiderivative of 1 over y is the ln of y, and the antiderivative of, with the plus c, we'll actually call it c1, because as we're going to find out, we end up really with just the c values being put together into one c value. But the antiderivative of 2x, of course, if you add the exponent and divide by the exponent, you end up with x squared plus c, and we'll call it c2. Now, at this time, what we can do is we can lump both of these c's together to be just one c value. With the magic eraser, all I'm going to do is say that we'll have our c value put together on the x side. And it's always going to be this way forevermore. Now, we've done the antiderivative, but the problem with this equation that we're staring at is it doesn't make a lot of sense because it's not solved for y. And so we need to solve it for y by doing some algebra. In this case, we want to do something to get rid of ln. Now, don't tell me that you want to divide by ln. You're not multiplying by ln. But what you do is called exponentiation. You actually do an e to both sides. This is an algebra trick. E is the base that cancels with that ln, and it leaves us with just y. And as you're going to find out, that's actually our goal, to solve the equation for y, and it's going to be e to the x squared plus c. Again, we want to make sure we understand that x squared plus c is now in the exponent. And that would be the solution of our differential equation. Now, before we move on to the next problem, just keep in mind what we did here. We separated the variables. That was the green and red arrow in the beginning. And then we did the antiderivative of both sides. It actually always works that way. So when trying to solve a problem like this, obviously it looks a little more complicated, but we still first want to recognize that all we need to do is get the x's on one side, so we'll multiply both sides by dx, and we want to get the y on the other side, so we'll divide both sides by 1 plus y squared. And by doing this, we will have the variables separated. Notice that the equation, it really does always come out the same way. With simple division, you always end up with 1 over 1 plus y squared. And with simple multiplication, we're obviously just going to end up with the dx on the other side. Now, this allows us to do the antiderivative, or the integral of both sides. And so once again, we have two problems to try to anti-derive. Now, the antiderivative of 1 over 1 plus y squared is of the form 1 over 1 plus x squared, meaning that it's going to be an inverse tangent. It's not x, though, it's y, so it's the inverse tangent of y. And when we look at the x side, we need to recognize that there's actually two functions here. That is that there's a 2x function and there is this e to the x squared function. Remember, you want to be thinking about using substitution. If we're going to use substitution, then we're trying to look for a u. And if we pick the correct u, we'll be able to discover that the derivative, in other words, du, is going to cancel with the rest of the problem. That's exactly what happens here, because this 2x is going to be able to cancel with this 2x once we do the substitution. So this is a substitution method built into finishing this separation problem. We're going to end up with the integral of e to the u, du. What you want to do is keep in mind that you actually have to do the antiderivative of e to the u. Of course, that ends up being the same thing. So when I write down e to the x squared, I've actually done the antiderivative. Now keep in mind that the plus c would be on the end of this, but still this e to the x squared right here, this is actually the antiderivative. Remember the step that we want to make sure we don't forget in the substitution method. Now this equation, once again, it looks kind of weird. That's because it's not solved for y. So you always have to solve for y, meaning you got to do some algebra. There's an inverse tangent here. To eliminate the inverse tangent, what I want to do is the tangent of both sides. I'm not multiplying by tangent, I'm just doing the tangent. And that leaves me with the tangent of e to the x squared plus c. Notice that the c is inside of the tangent. That's because of the timing of this algebra. All right, well, what if we wanted to solve this differential equation, x root y cosine squared of root y? Looks like lots of fun. So instead of me having all the fun, I'm going to encourage you guys to start the separation. This would be a good problem to push pause and see if you can start it. And then, of course, when you're ready, you can unpause and watch the next step. All right, now I hope you were able to divide both sides by the terms that had the y. We actually end up dividing by root y and the cosine squared of root y. You also just want to multiply dx the other side. That leaves us with two integrals to do. Now I'm going to be honest, the integral of this 1 over root y cosine squared root y, it actually is quite challenging. I'm going to be showing you how to work that out, but I would hope that you're able to do the antiderivative of x, if you want to think about that, and then we'll move on to dealing with the 1 over root y cosine squared of root y. All right, so let's not make this the integral of x too complicated. You add to x, you add to the exponent, so we end up with x squared. We divide by 2, we get 1/2 x squared, and we can put the plus c in on the x side. Now, integrating the y side, as I said, it's quite challenging. Let's take a look at it on a separate page. All right, now we have to recognize that there's two functions in this problem. There's a square root function and there's a cosine function. Now, if you feel like there's more functions than that, it might be an argument here that there's also two square root functions, but the bottom line here is that to integrate this, we're going to have to think about the substitution method first. Now, when you think about the substitution method, you try to identify a possible inside. As I say, a possible inside, many times that's the inside of the trig function, although one might argue that we could try to grab the entire cosine. The problem with grabbing cosine as the inside is that its derivative is opposite sign, and that's not going to cancel with anything. There's no signs anywhere. So we're going to let u equal the square root of y, and kind of one of those problems where we live and learn a little bit by being able to watch the teacher. But you're going to see here that the derivative of a square root does work out to cancel with the rest of the problem. We just want to be careful when we do the derivative that we subtract from the exponent. In this case, we end up with a negative exponent. Now, negative exponents often are rewritten as positive exponents. In this case, I'm going to even rewrite it as a 1 over a square root. The reason that I'm doing that is because there has to be something in you that sees that this 1 over the square root of y seems to be the rest of the problem. In other words, the part of the problem that's going to ultimately cancel. Let me show you how that works out. This is a good problem to be able to go through the steps where we actually isolate and do some rearranging. I'm going to take this piece, I'm going to multiply the whole thing over here, 2 root y du, and that's going to equal dy. I did change that to a dy. So we're going to take this and we're going to substitute it. We're going to also carefully keep the rest of the problem that is unchanged, that is the 1 over square root of y. We're also going to keep the cosine squared, and well, of course, now we're going to do a little bit of substituting. We're going to substitute the letter u in here, and as you're going to find out, our main substitution is to scoot this 2 root y du up here, which it's made to cancel. It's going to cancel with the rest of the problem. Now, I'm slowly but surely getting to a simpler integral, and that simpler integral is 1 over cosine squared, 2 times 1 over cosine squared, which we're able to, by some simple trigonometry, say that the 1 over cosine squared is the same as a secant squared. And so the problem ultimately becomes, what's the antiderivative of secant squared? Well, thank goodness that is a basic, that is kind of a memorized rule, and of course the antiderivative of secant squared is tangent. Now, when I write down 2 tangent, I'm doing the antiderivative. I'm also going to substitute back in the root y that was there for u, and we end up with our antiderivative, which we're going to, of course, copy back onto our separation problem. All right, so we've got our 2 tangent of the square root of y, which was, of course, the antiderivative. Now, we still need to solve this for y. It actually is going to require a couple algebra steps. Number 1, we have to divide both sides by 2. Really, you're dividing everything by 2, but when you divide c by 2, it just dissolves again to be a c value. When I divide 1/2 by 2, we actually end up with 1/4. So I'm going to go ahead and just make that quick change. We'll change this to a 1/4. Now, when we next we need to get rid of the tangent, so we'll do an inverse tangent of both sides. When you do the inverse tangent, nothing really changes, except, of course, that we cancel the tangent, but nothing really changes on this side of the equation. So we now have the inverse tangent of 1/4 x squared plus c. Notice that the plus c is on the inside there. And lastly, we're going to square both sides. When I square both sides, just to be safe here, we're going to do a big square on the outside of everything, which leads us with a final answer of the quantity of inverse tangent of 1/4 x squared plus c, that quantity squared. All right, now that leads us to our last problem for this lesson. It's an initial value problem. Really, it's just a problem where we're going to solve for c because we are given some initial value. We're basically given some information about the final answer. Before we get to that fun stuff, though, you still got to separate the variables and you got to do the antiderivative of both sides. Again, this is a good problem to start. See if you can get the sides separated. Push pause and pick it back up as you want to see each step of this problem. This really is just a basic problem because it's nothing more than one function that happens to have a negative exponent. But you can do the antiderivative of a negative exponent. Just add to that negative exponent. When you add to it, you actually get a positive 1/2. Don't forget to divide by 1/2. When you divide by 1/2, you end up with, of course, 2. So your antiderivative is 2y to the 1/2. ln of x over x is actually an interesting integral. You may remember that we did it a few sections ago with the substitution method. That is, if you carefully let u equal the ln of x. Now, the reason you would do this is because you know that the derivative of the ln of x is 1 over x. Of course, 1 over x has a lot to do with the rest of the problem. So these two parts here are going to cancel, leaving us really with see, students have to understand that in this problem, all that's really happening is we're changing the ln of x to be u. We already canceled the denominator. We canceled the denominator with the 1 over x. So the antiderivative of this problem ends up being a u squared divided by 2. Of course, it's really ln that's being squared, as that is the value of u. So we want to be careful here that we write this as the ln of x squared, which can be written in a little different notation. You can put the square up with the ln, but we want to substitute it back either way. Now, I like students to see that although you could solve this equation for y, you actually have the ability to plug e in for x right now, as well as 1 in for y. It might be easier to plug them in right now, since the equation is it's not so undone. It's just a little easier to evaluate each of these steps. You can evaluate the square root of 1. That's pretty easy. You can do the ln of e. Remember, the ln of e is equal to 1. So we're solving this for c, and it looks like that the left side of the equation will equal 2. Looks like that the right side of the equation will equal nothing more than 1/2 times 1 plus c. So we're able to subtract 1/2 from both sides and end up with a c value 5/2. Now, we have to keep in mind here that we're not done with the problem, even though we found the c value to be 5/2, and of course we can even substitute it back in. Now you have to get down to the dirty work of actually solving this problem for y. So we will divide both sides. We'll divide both sides by 2. And when you divide both sides by 2, there's actually some math that you can do here. And change the coefficient to 1/4, as well as changing the c value to 5/4. And then when we square both sides, we will have solved the equation for y. Be careful here. When you square both sides, you're not going to be able to do any more changing of these values. So we get 1/4 ln of x squared plus 5/4, that quantity squared, and that would be your solution. That's what's equal to y. Now I want to be clear that the technique of separation of variables, it's not easy. It wouldn't be easy if we were in the classroom or not in the classroom. These kinds of problems often students have questions on. Feel free to use my Google Meet offering. I'll be available. You can dial in. You can ask me questions. I'll work out a problem. I'll answer a specific question for you as you start to work on your assignment, which is actually on just a piece of paper. I'll provide that for you, and you can do the assignment on that paper, or you can just continue to do it in your notebook. But the assignment is on a paper, it's not in your textbook.